Hey everybody, today we are diving into convolutional neural networks, or CNNs for short. These powerful tools are designed to understand images by focusing on the relationships between pixels. What makes CNNs so cool is that they're incredibly efficient at processing images because they use shared weights and focus on small sections of pixels at a time. Plus, they are translation invariant, meaning that they can recognize an object regardless of where it is located in the image. For example, think of this simple grid of numbers as a tiny image. A filter slides over it, detecting patterns like edges or textures. This process shows CNNs to learn and recognize complex visual information. CNNs are used in tons of applications, from facial recognition to self-driving cars, and they're constantly evolving. Okay, so as we just mentioned, CNNs capture spatial features from images. I like to say that they can also be applied to other types of data, but mainly when we talk about CNNs, we are talking about image data sets. And the idea is that in this case, it's very important to capture spatial features, which in some sense means that we care about pixel arrangements and their relationships. There are three main types of layers that we are going to use in convolutional neural networks. The first one is obviously convolutional layer, and that's what really allows us to extract spatial patterns and have small windows or kernels that we can traverse through the image. And then we use something called a pooling layer, which is mainly used to reduce the dimensionality of extracted features. This is also important to make sure that we have properties such as translation invariance. And as we said, this means that if we really want to detect some objects or even some edges in an image, it shouldn't really matter where it is exactly located, right? So we want to have that translation invariance property. But something also very interesting about convolutional neural networks is that usually at the very end of the network, we have to use fully connected or dense layers. So these are the layers that we saw in the previous weeks when we talk about feed-forward neural networks, right? So that's something that we have seen, and we still have to use them here. And the way you can think about it is that, like, let's say we are working with MNIST images, right? Digit images. And in this case, if we have a 10-class classification problem, then we need to use a fully connected or dense layer as the output of the network, where we have one neuron for each class, and then we use the softmax scores as estimated probabilities. So therefore, we always have some sort of like fully connected or dense layers as the final layers of a CNN. So what are the advantages over, feed-forward neural networks, or in particular multi-layer perceptrons? Well, the first thing is that we have to use fewer parameters, right? Because in this case, as you're going to just see here, we're going to have one kernel or window that we share across the image. So we are not introducing too many parameters because of the high dimensionality of images. And then the other property is translation invariance, which means that we want to treat all patches of the image uniformly, regardless of their position. And then the third one is locality, right? Because it means that, especially in the context of image processing, we usually want to work with the small neighborhoods of pixels to compute hidden representations, right? So we don't necessarily want to look at just global features. We also want to have local features as well. Okay, so I mentioned a lot about convolutional layers and the idea of using fewer parameters compared to dense layers. So how is this possible? So this is an example to demonstrate this. Let's say your input, which is this image right now, it's a very simple kind of like, or a small image of height 3 and width 3. And now you have a kernel, also this is known as a filter, of size 2 by 2. Okay, so now we want to perform this convolution operation. So the way you do this is that you take this kernel, you put it on this very top left corner, and you start doing element-wise multiplications and then add everything together, right? So this case means that you're going to multiply 0 by 0, 1 by 1, 3 by 2, and 4 by 3, right? So we get 12 plus 6 plus 1, which is 19. And then in order to find the next value, you have to shift this kernel one to the right, right? So this means that now this area would be the second position that we have for this kernel. And the same thing for this bottom row, right? So what you do once you have this kernel here, you can shift this 1 unit down. Then you have 0, 1, 2, 3 placed on top of 3, 4, 6, 7, and you do the multiplication element-wise and add everything together, which you should get 37. And then you're gonna again shift this 1 unit to the right, and in this case, you should get 5, 24, and 14, and that's hopefully 43. Okay, so that's how you do these convolutional operation. And as we said, the nice thing is that, like, let's say right now, I'm providing the values for these 4 elements of this kernel, but in real world, we need to find the optimal values. So in this case, we are using these 4 values for the entire image or input, rather than introducing one new parameter for every single element that we have here, right? So that's the idea of sharing weights. And in general, a convolutional layer is made up of a large number of convolutional filters or kernels. And convolutional filter, as we just mentioned, relies on very simple operations. So you do multiplication and then addition. And here you can look at some kind of like general formula, right? So let's say now, instead of working with that 3 by 3 input, let's work with an image or input, which is 4 by 3, right? So we use this indexing to show the index for the row and column, right? So we have A11 through A43, row 4, column 3. And let's say, again, we have this 2 by 2 filter. So the way that this will work is that you're going to start from this top left corner. So you do the element-wise multiplication and add everything together. So you get A11 F1, A21 F21, and A12 F12, and then A22 F22, okay? And then you have to move this 1 unit to the right, okay? And that's where you get A12 F11, A22 F21, right? And plus 2 other terms, and you add everything together. So this means that in this case, if we have this 4 by 3 image or input, and we have a 2 by 2 kernel or filter, the final result is of size 3 by 2, right? We have 3 rows and 2 columns. So how can we find the size of this convolutional operation? So this actually has a general formula. So if the input is of size nh by nw, so h represents here height and w represents width, and the convolution filter or kernel is size kh by kw, then the size of the final result or the output is n minus k plus 1 in both dimensions. And you can easily verify this, for example, using this very simple example that we have here, that this formula is actually correct. So what this means is that one of the implications is that whenever you perform this convolutional operation throughout the convolutional layer, the size of the output is slightly smaller than the size of the input, right? And that's exactly how smaller it is, right? We always have this minus k plus 1. So if, let's say, k equals usually like 3 or 5 in general, then means that, -3 plus 1. So that would be -2. So that's, how much we are going to reduce the size of the input after the convolution operation. In order to avoid this, one thing that you can do is to use this padding. And what this means, it's a very simple idea. You're going to add extra rows and columns of zeros around the input data before applying the convolution operation, right? So we have an example of this, right? So we have that input image of size 3 by 3, if you recall. And now we add these extra rows and columns of all zeros, right? So this is called the idea of padding. And if you look at it across the height, we have this padding of size 2, so 1 on each side. And the same thing with the width, right? So we have one column of zeros here and one column of zeros here. So that means that in this case, we are going to do padding of size 2 across both height and width. And it is very easy to show that in this case, that when you do this padding, if we have this pH as the total number of rows of padding that we have added and pW as the total columns of padding, then the size of the output after the convolution operation is, this is the new height and this is the new width, right? So the only difference here compared to what we had before is that you have to add that pH and pW to each dimension. And what this means is that if we want to retain the size of the input, meaning that after the convolution, we have the same height and width, then the padding parameters should be always the corresponding size of the kernel minus 1, meaning that if you want to, let's say, use a filter of, let's say, size 3 by 3, then the padding should be of size 2 across both height and width. And this is one of the reasons that convolutional neural networks, when you look at multiple examples or existing architectures, it's very common to use odd values for the height and width of the kernel, because then when you subtract this one, you end up with an even number. And this is nice because then you can do padding equally on both sides, right? So in this case, you can see when we have padding of size 2, I can do one padding on one side and one column of padding on the other side. So we don't have to determine which side we have to do more padding. So that's a nice thing about odd values of kernel height and width. And then the other thing which is very important when you're working with convolutional layers is this idea of a stride, right? So what I explained so far is that when we have this kernel here, right, when I place it here to do this convolution operation, I always move this to the right and to the bottom only by 1 unit, right? But we can obviously change this, and we can, for example, move this to the right by 2 units or 3 units, especially if you have a large input or image, right? So that's the idea behind a stride, which means that how much the filter shifts both horizontally and vertically between successive applications to generate the output in this case. And a stride of 1 means that the filter moves 1 pixel or 1 unit always horizontally and vertically at a time, so there's no skipping. But if you use a stride value greater than 1, this means that then you are going to skip some pixel. So this is a very nice way to be able to control the size of the output. And you can actually show that the general formula right now, if we have both padding and a stride with SH and SW to show, the stride for the height and width. And P here is the padding and is the size of the original input. This is the general formula that we have. So obviously if SH and SW, they're both equal to 1, we get exactly the formula that we have here. And this is now a more general case where SH, for example, can be 2. Right. And a general rule of thumb is that if, let's say, a stride is equal to 2, means that you're going to reduce the size of the output by a factor of 2, right? Because then you have this whole thing divided by 2. It's not exact because also you have SH added to the numerator. But, if, let's say, hypothetically, n is large number, meaning that you have a large dimensional like or a high resolution image, then you can kind of like approximately ignore this sh in the numerator, and you only have this sh in the denominator, which means that if now you increase sh by a factor of 2, then the size of output will be decreased by a factor of 2. So this is a general rule of thumb that, if you want to make sure that your output has the same size as your input, then you can adjust the padding according to this formula. And if for some reason you want to decrease the size of the output by some factor, then that's easy. You can use a stride. And here you can see an example of case where we have this padding, and also we have a stride of 3 and 2 for height and width. So a stride shouldn't be same across both, but you can see that in this case, in terms of height, which is this vertical direction here, we are using padding of 3, which means that first we are here, and then we are going to be here, and that's if we do 2. And since we have a stride of 3, we'll directly come to this point, right? So that's why this one is blue. And then since across the width, the stride is 2, right? So first we are here, and then we're going to go 2 units to the right, which takes us here. And obviously then we have another case where for this one that we have in this area, we go 3 units, right? We go 3 units towards bottom here, and we get this case that we have here, 8. Okay, so I stop here a little bit so you can confirm this, just to show what you get exactly 8 here, because when we put this in this location, you can see that the only thing that we have to calculate is this 8 times 1, which gives us this 8 here. Okay, so that's how we get this 8 in the bottom right corner. After talking about like these important parameters, including the kernel width and height, padding and stride, and how that will impact the size of the output, now we can talk about cases where the input has more than one channel, right? This is very important because in many cases when we talk about images, input images are actually 3-dimensional tensors, meaning that we have height, we have width, and then the third dimension or axis is the number of channels for a color image, that's RGB, right? Red, green, and blue, right? So we are not just working with 2-dimensional arrays, which correspond to grayscale images. And in many cases, we do actually have more than one channel. And in order to understand how this works, this means that now the image that we had before, that we gave you a formula for, now has this 2-dimensional structure for each channel. So one thing that is easier to use here, I'm using this superscript to denote the channel number. So you can think of these, that if we have C channels, we have C of these slices, right? So it's going to be a 3-dimensional tensor, but right now I'm just looking at one of those slices. And in this case, our kernel or filter should also have the same number of channels. Otherwise, we cannot do the convolution. And once we confirm that that has the same number of channels, then we perform the multiplication, which is element-wise, and addition for each channel. And then we add this result across all channels. So here, I revised the formula that we had before to account for the number of channels. So it's exactly what we had before, if you recall. The only difference is that now I use this superscript I, and I do this summation I from 1 to C. So that's something very important to remember here, that if you have an image or input that has multiple channels, like let's say has 3 channels, then the kernel or filter must have the same number of channels. Then you do the element-wise multiplication across all channels, do the additions, both across one slice and across all slices, right? That's why we have all these terms added together. And the result will actually be a two-dimensional tensor. Okay, that's something very important to know here. So here is an example of this, right? So input has two channels, right? The front channel and the back channel, okay? And the kernel is the same way too, must have the same number of channels. So now what you do is that you're going to have in the back channel here, you have 1, 2, 3, 4, 5, 6. So that's what this back one is, this one. And here also is 1, 2, 3, 4. I know it's hard to see, but that's like the back channel of the kernel is 1, 2, 3, 4. So you're going to do these multiplication element-wise, do the addition, and the same thing for the front channels, right? You can easily see this. So that's like the whole front channel of this input and this front channel of this kernel. You do the multiplication, and then you add everything together to come up with these two-dimensional tensor, right? Again, height and width. So in some sense, we lost that axis that corresponds to the number of channels, right? That's the way I like to think about this. So now the question is this, right? So we might have an input image which has three channels. We perform some convolutional operation, and we end up with a two-dimensional tensor, right? So what if we want to also have multi-input tensors or multi-channel tensors in the middle of our network? Is there any way to actually control the number of channels? And the answer is yes. You can actually control the number of channels in your output, and that's based on the number of filters that you have. So before talking about the kind of like the math here, so the way you can think about it is that like if your input has three channels, right? Each kernel must have three channels, and then you perform your operations as we just explained. So that would be like the lighter blue kernel that we have. But now for this one, the one that we have here, the one like, let's say a little bit more bluish here, now you can have a separate kernel or a second kernel, and now you perform exactly the same operations. And since each one will give you a two-dimensional tensor, now you have two two-dimensional tensors, right? So this means that now your output actually has two channels, right? And if you want your output to have, let's say, 10 channels, then you need to have 10 distinct kernels, right? And each kernel must have itself three channels, right? Because otherwise you cannot perform the operation. But in this case, as I just mentioned, if we have two, we can add like, let's say 8 more. So we have 10 of these kernels, and then we will end up with 10 channels for the output. So here is the general formula that you can keep in mind, right? So let's say you have a kernel with height kh and width kw, right? So that's kind of like the front face that we have, height and width. So each kernel, in fact, should be kh by kw by ci, where ci stands for the number of channels for the input, right? So here, for example, number of channels for the input is 3. So that's how each kernel is. And now if you want to, let's say, have CO, and here O stands for the output, right? If you want to have CO channels in your output, then technically the total size of your kernel is KH by KW by CI by CO. So you get a 4-dimensional tensor or array here for these kernels that you use. And as you can see here, the output, the height and width, we can use the formula that we just had before. And in terms of number of channels, we get CO channels. So that's all you need in terms of how to perform convolutional operation if you only have two-dimensional tensors. If your input has CI channels, you know that the kernel should have CI channels. And if you have multiple channels for your output, then you have to use distinct kernels. And that's kind of like the general formula for the kernel size for a layer. So the next thing we want to talk about after talking about convolutional layers is about max pooling. So that's kind of like another very important idea is that the idea behind pooling is to reduce the dimension of the input and or in other words downsample the spatial dimension. And this is very helpful because first we're going to reduce the size of data that we propagate through the network, and second it helps with that translation invariance that we just discussed. And max pooling, in fact, it's a very simple idea, right? So what you do is that if it's a 2 by 2 kernel, we really don't have any weights here. It's just a simple maximum operation, meaning that we're going to just look at this 2 by 2 neighborhood or window, and we say that what is the maximum value? The maximum value is 4, right? And then we shift this to the right by 1 unit because right now let's try this one. And what is the maximum here? It's 5. And if we shift this down 1 here, it's 8. And technically we had to take this, blue window first down and then shift it to the right. But I just wanted to kind of like make this faster. And if you look at this area, this 2 by 2 on the bottom left, you can see that the max is 7, right? So that's how you can really easily like reduce or downsample the dimension of the input. There are other types of pooling too, for example, like average pooling, which is taking the average of all the elements in the window. But these days, max pooling is way more common than other types of pooling. So with this, we are very much ready to actually show you how this works if you want to implement this in Keras. So we're going to import NumPy, we're going to import Keras, and also we're going to import layers, which is part of Keras. Okay. So in this case, what we are doing is that we are working with the MNIST handwritten digit data set, and this is built in Keras. So we can easily load this and get the training and testing data set. As always, one thing that you can do, which is very popular and important, is because the original inputs or pixel values are from 0 to 255, we can divide them by 255. So in this case, they're scaled from 0 to 1. This is very helpful to make sure that we don't have to be worried about storing very large values, throughout our transformations that we perform. And we do the same thing exactly with the test data. And then the other thing that we are going to do here is that we want to make sure that these images are actually 28 by 28 by 1. And the reason for this is that when we talk about convolutional neural networks or CNNs in Keras, the assumption that we make is that each image is 3-dimensional. So the number of the height, the width, and the number of channels. Since MNIST dataset, it's pretty old data set and it's a grayscale image. We don't really have 3 channels. So, hypothetically speaking, we can kind of get rid of the third dimension because there's nothing there. It's just one layer or one channel. But, that's something important to make sure that we actually add this one here. So we tell Keras very explicitly that, hey, we do have the third dimension, which is the channel number, but we only have one channel. So it's kind of boring because, we have a grayscale image. And in this case, we can look at, like, let's say the shape of the training data, right? That's what we are doing here. And you can see that in this case, we get these 60,000 data points, right? And each data point is here 28 by 28 by 1, right? So before in the previous lecture, we vectorized or flattened this because we didn't know about convolutional layers. And this was 60,000 by 784, which is 28 squared. But now you can see that now we have this 4-dimensional tensor as our input, which is the total number of training data points or the total number of images, and then height, width, number of channels. And you can see that we have 60,000 training samples, 10,000 testing samples. The other thing also from Keras, we use this 2 categorical to make sure that we actually have categorical outputs or one hot encoding of outputs, right? So in general, these training labels or testing labels that we have, they're digits 0 to 9. But since we are working with softmax scores and estimated probabilities, it's nice to just get this into the one-hot encoding, which means that in this case, for example, this belongs to 0, 1, 2, 3, 4, 5, right? So that belongs to digit 5. And here you can look at one of these images, right? So obviously the reason that, you see the color here because I have to put C map. So I can put that C map equals gray. So just to make sure that this is actually a grayscale image, that's I think a little bit better. So you can see that this is like one of the images that we have here, and this is indeed digit 5 as we expect, right? Because that's what it shows here in terms of the label in the form of one-hot encoding. But you can look at other images too here, so you can see that this is like an image of digit 0, or here they have like digit 2. You can see some of this can be really hard to even like distinguish just by looking at them, but let's put this back just to make sure this is consistent with what we have here. And remember, we have 60,000 of these images for as the input for training this model. So we're going to use the sequential model here, although we talk about functional API too, so you can always develop some more complex type of CNNs as we discussed using the functional API. But for now, we're going to use this Keras.input to say that this is the input layer. And remember, the input shape, it comes from here. So in this case, it's important to say that this is 28 by 28 by 1, because we want to provide the height, width, and the number of channels. And then we have this conv2D. So this is the 2D convolutional layer that we just discussed. This is the kernel size, height, and width. And also, this is the number of the kernels that we use. So now we know that the number of kernels determines the number of channels for the output. And the one thing that I didn't discuss is that once we do this convolution operation, where it's in the form of of element-wise multiplication and then summation, then we can also apply some nonlinear activation function, very much similar to multi-layer perceptrons. So that's where this activation function becomes important, right? Because we want to make sure we introduce also some nonlinearities, and that's how we do that. We have two pooling layers. These are kernels of size 2 by 2. And then after performing some convolution and max pooling, now we're going to flatten or vectorize everything, because the goal is that by now we have extracted these spatial patterns. In this case, also, we're going to use something called dropout, which is very useful for regularization. So what it does here, you always provide a probability, and this is a probability to randomly shut off some of the neurons. So the idea is that we don't want to have one or two neurons in the model that really carries a lot of information and weight. So we want to kind of randomly turn them off, right? So we know that we don't rely on a very specific subset of neurons. So that's the idea behind dropout, which is for regularization. And then for the last or output layer, we use dense, right, with 10 classes and softmax because we want to have estimated probabilities. So we can see that here, the size of the input image after each operation, you can confirm this using the formulas that we have. After the first convolution, we get this 26 by 26 by 32. Why do we have 32 channels? Because we have 32 kernels here, right? It's exactly what we just discussed. So I'll definitely recommend you to use those formulas that we provided to make sure that that is consistent. Okay, so now we can see the total number of parameters here, which is about 35,000 parameters. We also have to set the batch size, the number of epochs. Since we're using the one-hot encoding already, so we are going to use categorical cross entropy. We do not need to use a sparse categorical cross entropy because we already used one-hot encoding. Use the Adam, and then for metrics we use classification accuracy. All right, and then we provide the training data, which are these X train and Y train. We also set aside 10% of data for validation, right? So that's the validation split. So if we run this, so you can see that in this case, Let's get through the first epoch. So we started from 89% accuracy. So we already started from a very good result. And then this, you see that, very slowly reaches to 97, probably 9.98, which is really great. So in fact, MNIST data set now is a very standard data set in the sense that you should be able to get close to 99% accuracy, but you see that even this simple model, without doing much fine tuning or hyperparameter tuning, it is getting a really good result, right? So this is the important part about using convolutional neural networks, because first, they definitely reduce the number of parameters that we need to use, right? Because they're using this mechanism to share weights. And at the same time, we also extract local patterns. So we can see where we end up eventually. So in this case, we see that we get about 99% accuracy on the training data, and on the validation data, the same thing too. So this is very common for this data set. To get about 99, you should be good, very close to 100% accuracy. And obviously, you can evaluate your model on the testing data as well, right? Because this here is on the validation data. That's why it's called validation, the 10% that we put aside. But we do have a test data we've never used. And you can see that in this case, even on that data set, we get 99% accuracy. And the loss is 0.02, which is great. This is a cross entropy loss that we have seen before. And that's very much like comparable to what we have for the training data. And the loss that we calculated on the training data, and the loss we calculated on the validation data. So that's all about convolutional neural networks, and I hope you found this video helpful.